So the first talk is going to be given by Nick Rhinehart. And you see the list of, no, you don't see yet the list of his co-authors. The talk is about PRECOG, prediction conditioned on goals in visual multi-agent settings. Go ahead.
Thank you. Okay, good. All right, we're live. Hi, everyone. I'm Nick Rhinehart, and today I'll talk to you about some of our work on forecasting in partially controlled multi-agent settings when you have some visual observations. So there are many settings in the world that generally involve a complicated interaction between agents. We want to automatically capture these complicated interactions in order to predict future behavior. So this video that I'm showing here is a demonstration of our approach to predict the future motion of many agents in real traffic scenarios. In many mobile robotics settings, the standard pipeline involves forecasting without knowledge of the controlled agent's intentions. However, in these settings, we generally do have this knowledge of what we want our robot to do. So we have control over the robot's intentions. Our framework has the capability to leverage this additional source of information to inform its future predictions. So by incorporating knowledge of our own controlled robot's intention, we can reason about how other agents might respond to our intentions. And so I'll show that this enables us to forecast what other agents could do with greater accuracy. So in our application, that means we can better forecast what other human-driven vehicles are going to do, given knowledge of our own autonomous vehicle's goal. So it's critical for us to model and evaluate the approach in terms of joint behavior. So let's look at this simple problem with just two agents. And imagine that I'm driving this blue car here on the left, and I want to turn left. If the orange car gets in my way, I need to react to their behavior in order to avoid some bad joint behavior like a crash. Because the agents are codependent, we need to both model and evaluate the data with this joint interactive behavior in mind. If we don't model any future interaction between them, individually likely behaviors can yield unlikely joint behaviors. So if I evaluate the forecasts on a per-agent basis alone, the evaluation is going to fail to penalize situations that rarely occur in the data. The takeaway is that you can't independently model or measure forecasted behavior. You have to measure it jointly. So now I'll relate these outputs to the graphical models used to create them. The model on the right correctly captures interactions at every time step between each agent. And here there's just two agents. So this allows the forecasted agents to sequentially react to each other. The model on the left, however, incorrectly decouples the future decision-making of the agents. All right, so we don't want to use this model here on the left. Let's talk about how the model on the right can be used in several different ways to forecast behavior. So here's an example of some standard multi-agent forecasting with this model, with that graphical model I showed on the right. So we can make joint predictions for where all of the cars are going to go. And the paths marked with circles indicate a possible future motion. And the paths marked with triangles indicate some past positions. And if you can't see the triangles for a vehicle, that just means the vehicle was stationary in the past. Okay, so this is the standard forecasting setup where we are just predicting where everyone is going to go. But now let's leverage the fact that we have control over one of these vehicles, that blue car 1. We should use knowledge of this car's intention when making predictions about the future behaviors of the human cars, so the non-blue cars. And the approach I'll describe to you lets us do this. We can set any agent's intention and then consider how that would affect the predictions of the other agents, how they're going to respond. So for instance, if we control this car here to drive faster than it would otherwise, you can see the green human car 3 is predicted to move faster than it would otherwise. However, if we plan to instead make that car 1 stop, so we're setting our future intention to stop, the human car 3 is predicted to stop in response. These predictions show that the model captures aspects of the interaction between agents. And it's learned this purely from demonstrations of joint behavior. So now I'll talk about how we make both types of predictions. So in order to capture aspects of joint behavior, we need to model stochastic decisions of every agent in the context of some scene. So we have some scene context. Let's say it's some overhead picture of the scene, and we're trying to predict the future trajectories. Now, we factorize the model over agents and time and provide it with this context. And this factorization property is key to implementing the conditional forecasting capability of the approach. The latent states at each time step for every agent correspond to an agent's control of the next action that it can take. Its next state depends on the control and the most recently predicted states of itself and all of the other agents. So in our two-agent model, if we have some decided latent values for one of the agents of the robot car, then we have specified how our robot is going to react to what it sees in the future. In order to perform this conditional forecasting, we want to choose those latent values for the robot, the latent z's, that takes the robot's goal into account. So we're going to feed it some goal and choose those latent z's that usually land it at that goal. Once we've chosen those z's, then we can take the z's, or the latent decisions for everyone, and pass them through the forward inference procedure of this model to get this output joint trajectory. So the process requires 3 steps. We first have some planning objective where we're looking for those good values of our z's that satisfy some goal g. Then we are going to sample the latent decisions for the human. We don't know what the human will do, so their behavior is stochastic. And then we feed the resulting joint latent values into the forward inference procedure, and that yields us some predicted joint trajectory for all of the agents in the scene. So how can we, I skipped over what this objective exactly is, so let's talk about that soon. So again, because these latent states for an agent correspond to the reactions that we choose for the controlled agent, deciding them, again, corresponds to a plan for how the agent is going to react to the other agents. So this doesn't determine the resulting trajectory, as it's still affected by the uncertainty of the other agents. So we don't know what the other agents are going to do, so we have to be robust to the space of things that they could do. How do we design these good plans? How do we choose this objective? Consider building a posterior that measures the probability of some joint trajectory given this goal information. So we're going to plug the goals in as given information. However, again, because the human behaviors are random, this loss is random. So we need to make it deterministic. We are just going to take the average case over, one way to make it deterministic is to just take the average case over the other agent's behavior and optimize that instead. Then if we apply Bayes' rule, we get these 2 terms. One is our prior of learned behavior. So we've taken a bunch of demonstrations of behavior in. We've learned to predict what normally happens in the future. And then we have this goal likelihood term, which is where we're incorporating the intentions. So what's an example of that goal likelihood? For instance, we could just put a normal distribution about a specific point. And then it's going to penalize our latent plans if they don't normally land us near that point, near the mu of the normal distribution. Okay, so now if we go back to our original example, all we did here was put this normal distribution about our intentions, and then we ran the planning procedure, we got the latent z's for the robot, and then sampled what the other agents would do, and we see that they react to our intentions differently. Okay, I'm going to maybe skip a little bit over some of the details of the model. Essentially, basically the model in our domain. We have two input contexts. One is the past positions of all the agents. Another is the information about the scene. And in this case, we're just going to be using LiDAR features. And then, so we process the LiDAR with a convnet. We process the past positions with an RNN. And we have this RNN, another RNN for every agent that then produces sequentially the predictions for all of the agents. So skipping that. OK, again, we saw this already. So note that basically we've learned this model Q that we're using in that objective L. And as part of the model, we have the forward inference procedure F. So again, PRECOG is 3 steps. We first plan our latent Zs. We then sample the latent Zs of the other agents, and then we pass them through the forward inference procedure. Here's some examples of this PRECOG prediction in some real settings. So on the top, conditioning the predictions on the robot goals yields a sample batch where the other car moves to take up space that is otherwise that is now vacated by the close following robot. So here we have no goal on the left. In the top right, we have this goal to sort of stop, and you see the other agent says, OK, now sometimes I can go where that agent otherwise was. And then in the bottom example, we're sometimes moving forward and then saying, OK, let's condition on me stopping, and then we see the vehicle behind us is stopping. And so the takeaway experimentally is that we were able to make better predictions of what the other agents were going to do once we observed the robot's true intention in some real data. So when we have some controlled agent, we use its intention to predict how the other agents are going to respond. And then we also ran the standard forecasting task and found that we outperform some of the state-of-the-art methods. So here, there's plenty of examples in the paper that I encourage you to check out. And I think I'm out of time here now, so I'll move on. I'm the end. That's the end. Thank you.
Thank you, Nick. We have 2 minutes and a half for questions. Please go to the mic. There's a mic there.
Yeah, sure.
Nice talk. How do you specify what the goals are? Are they like XY positions, or are they more abstract things like keep distance from obstacles?
Sure. In this work, they're just XY positions that we're using as the mean of this normal distribution that we're using as the goal likelihood. But we have some other work where you can specify goals as regions. So you say, I want the vehicle it's going to be somewhere over here. And then you can also use that for the planning procedure. So you can kind of plug in any distribution you want as long as it's kind of in the space of feasible goals for the expert.
And presumably you do like continual replanning, so you roll ahead, predict, take a step, and then repeat?
Yeah. So,
okay.
Right, in this, we're purely forecasting. In some other work, we're actually doing receding horizon control using something like this.
Okay.
Yeah.
Thanks.
Okay, thanks.
Thank you. We're out of time, so let's thank the speaker again.
Thank you.